the three ways to solve a problem in math are graphically, which that's what we did yesterday. We found limits using the graphs of the functions, right? Graphically is you just graph and you look at what the answer would be. The second way is numerically, and we kind of did that yesterday. That's a little bit more like mundane. So this one was a numerical approach where you keep plugging in like sequential points into a function until you see a pattern, and that's how you could come up with a solution. So graphically, numerically, and then the third way is analytically or algebraically. Those are the same words, analytically or algebraically. That's what we're going to do today, is we're going to evaluate limits analytically, okay, or algebraically. All right. So let's talk about, first and foremost, the properties of limits. Okay, so look at this. Suppose you have the limit as x approaches c of k. Now, when you have something written like this, okay, the way the notation is, you have the limit blah blah blah, and then whatever this is, that's the function. Okay, so if I have the limit as x approaches c of k, that's another way of saying that this is y equals k. You know what, since there's nobody today, why don't you come sit here so you're closer? Thank you. Here. Okay. So the function here is y equals k. All right. So let's see an example here. This is x, this is y. All right. Here, if this is k, that's what y equals k looks like, right? So imagine, for example, you had y equals 5. Well, what would that look like? This is 1, 2, 3, 4, 5. You have a horizontal line at y equals 5. Okay? So suppose you have a value here, this number c. As you approach that value from the left, what value vertically is your graph approaching? Tell me, raise your hands, tell me. Elliot. As you're approaching c, what vertical value are you approaching on the graph?
For the top or the example?
For this one, this is the graph of y equals 5. As I approach c, what vertical value is that approaching? 5. Okay? As I approach c from the other side, this is approaching a value of 5. So the limit is just 5. So if I have, you know, y equals k, and this is the point c, as I approach c, y equals 5. I'm sorry, k. As I approach c from here, y equals k. So that's my first property, that when this is a constant, the limit is just that constant. Okay? Yeah. So for example, look at this one. I have the limit as x equals 2 of 3. So you see here, it's y equals 3. Okay? No matter where you are, your y value is always going to be approaching what number?
3.
3. So this is just 3. Okay? Next, look at this one. The limit as x approaches c of x. What's the function here? Y equals what?
X.
Y equals x. Okay? So now, let's graph y equals x. That's what it looks like. Now, as I approach, please raise your hands for this one. As I'm approaching x equals 5, what y value is the graph approaching? What y value is the graph approaching? Tali, what do you think? What y value is the graph approaching? At x equals 5 here, this is y equals x. At x equals 5, what y value is the graph approaching? X or what? How much? 5, right? As I go to, so suppose this is -2, right? As I approach x equals -2, okay? Aiden, what y value is this approaching? So this is y equals 2. This is y equals x, right? When x gets close to -2, what does y get close to? -2, right? Because this is the function y equals x. So look, when x is 1, what's y here? 1. When x is 7, what's y here? When x is -14, what's y? -14. So as I'm approaching x equals 1, what does y get close to? 1. Okay? So when you have y equals x, as x approaches c, the limit is just c. So now take a look at this example. The limit as x approaches 3 of x will be what? 3. Okay? So those are the two basic properties. Now, here are some more properties of limits. Suppose you have two functions, and the limit of f of x as x approaches c is L. The limit of g of x is m. Okay, two different functions. One has a limit of L, one has a limit of m. Now look at what you're doing here. When you take the limit of the two functions combined, add it to each other, all you do is add the limits. Okay? And then when you subtract, all you do is subtract the limits. And then the same with multiplying. You multiply their limits. Okay. Here, if you have the limit as x approaches c of k times f of x, so what does that look like? So for example, suppose you have the limit as x approaches 4 of 3x. Look at this. Look at my function here. It's 3 times another function x. If you feel like you're not getting this, it's fine. Just, it's gonna be very, very clear in a few minutes. Okay? Let's just stick with it. Okay? Look at this one. I have 3 times x, right? What I can do is I can take out the 3. So now this is 3 times the limit as x approaches 4 of x. Right? So now look, let's hold back with the 3 for a minute. What does this give you? The limit as x approaches 4 of x. That's 4, right? So that's just going to be 3 times 4, 12. Okay? Quotient rule works as well, and so do the power rule. I'm not going to go at length with these. I'm just going to put them in practice right now. All right? These are very, very straightforward once we do them. Okay, so let's use some properties of limits to do this. First off, what do you think about this one? Oh, we just did this up there, didn't we? Yeah. Yeah. So what was this? 3. Okay, now look at this one. The limit as x approaches root 2 of e. What the heck? What is e though? It's just a constant, right? So this is just y equals e again. It's like whether it's e or 3 or 7,000, it's the same. So it's what? E. Because we have a horizontal line at e. Yeah. Okay, now here it says use the properties of limits to evaluate the following. Right, exactly. So now look at what we're going to do. The function that we know how to calculate is limit of x. Here I have 6 times x squared, 6x, and then 3. So here's what we're going to do. We're going to split this up. We're going to split this up because if I'm adding 3 functions, 3 terms, I can find their limits separately. So x approaches 4 of 6x squared minus the limit as x approaches 4 of 6x. No, because I put the minus there. The limit plus the limit as x approaches 4 of 3. Now, what I know is just x. and x. So I'm going to take everything out and just leave the x with the limit. So I'm going to pull the 6 out. So this is limit as x approaches 4 of x, and the power rule says I could square it. Right? Yeah. So 6x squared, 6 times the limit of x squared. That's the property that lets me do that. Minus, pull the 6 out, like this, plus, okay? Now look, how much is this? This I know exactly what it is. How much is that? 4. And now I have 6 times 4 squared minus 6 times, how much is that? 4. Plus, how much is that? 3. And in the end, it's, I have 75. Okay? All right? Right. Okay? So now, what type of function is this? This is a polynomial function here. 6x squared minus 6x plus 3. Okay. If you have a polynomial function, you don't, good news, you don't have to do this every single time. If you have a polynomial function, all right, then the limit is just P of C. Whoops. What does that mean? That means to find the limit, you know what? I don't have to do this. All I have to do is plug in 4 into there. That's it. Okay? In essence, that's what it tells me. So basically, use direct substitution to evaluate the polynomial. And that's what we're going to do. Okay? If you have a rational function, what were rational functions? Like, you know, f of x is equal to x squared plus 5 over x minus 4. Look, I have a polynomial divided by a different polynomial. Same thing, right? I have a polynomial over another polynomial. As long as the polynomial on the bottom is not going to go to 0, okay, then you just do direct substitution again. Okay? Easy peasy. All right. So let's do this. I have the limit as x approaches 2 of that. All I'm going to do is put in the 2 in my function, and that's going to be it. The only thing you have to watch out for is that denominator does not go to 0, because then everything just goes down the drain. Oh, things bad things happen. But we're going to go through it. We're going to go through it. Okay. Okay. That's the whole point of this. Like, this is, you know, nothing so far. Yeah. So, all right. So we're going to put in a 2. Okay. Here it is. Rule of limits. When you're dealing with the variables, when the variables are in the function, you always have to put that limit symbol. The second you substitute values in there, you must drop that limit. Okay? So this is going to be equal to, no more do we write limit. We just say 2 minus 3 over 2 times 4 minus 2 minus 15. And that's negative 1 over negative 9, 1/9. Do we simplify? Of course we simplify. But notice the limit symbol went away. Okay? All right. Here. Okay, so this is not a polynomial function. It's a square root function. However, as long as you can get a defined value, you can put x in there and make it a direct substitution problem. So this is going to be negative 1 plus 3 in the square root, root 2, and that's good enough. These are going to be on the non-calculator section anyway. Okay? Okay. Okay. Let's do this. What do we get? Negative 2 under the square root. It's impossible. So now we are saying that as x approaches -8, y approaches the square root of -2? That can't happen, okay? Let's think about this for a minute. What does this thing look like? This is the square root of x plus 6. So my vertex is here at -6, or my end point is here at negative. Huh? Right. There isn't even a graph there. So as I approach -8, there's nothing there. That's barren country. Like there is nothing happening over there, right? So this is DNE. The graph doesn't even exist there. Okay? Here, we're going to substitute just a, because a is a number, a is my constant, into the x's. So I'm going to get 2a squared minus 5a plus 3, and that's it. That's it. No. Okay. Indeterminate form. Sometimes when I have a rational function and I put in my x value, I get 0 on top over 0 on the bottom. Bye. Okay? So look, when direct substitution results in 0 over 0, all right? Okay, what's 5 over 0? It's like infinity or undefined. Okay, DNE. 5 over 0 is close to infinity and it's undefined. 0 over 0 is not the same as 2 over 0 or 5 over 0 or -3 over 0. A non-zero number over 0, infinity, undefined, that whole thing. 0 over 0, not that. When you get 0 over 0, this is called indeterminate form because it's impossible to determine the limit of the function at that point as things are, okay, the way they are now. When you get 0 over 0, you have to do some other things to it. And it's a surprise. Sometimes you will end up with infinity or a plain old DNE, or you know what? Sometimes you will get a very well-defined number, 4, okay? So that's why it's called indeterminate, because it's impossible to determine, okay? So you get that when it's 0 over 0, all right? So it's necessary now to use other methods to determine limits. It's possible that the limit exists, in which case we say it converges, remember that word? Converges to a certain value, or it diverges to negative infinity or positive infinity. Okay, I love these. Okay, so there are, how many ways are we going to go through? We're going to go through 2 different ways of evaluating when you have indeterminate form. Way number 1, okay, the first way is factoring. Oh my God, do I love these. Okay, so look at this one. Okay, I put -2 into this function. Okay, so substituting x equals -2 gives 0 over 0. So now I look at this and I go, okay, you know what, polynomial, why don't I try to factor this guy? So that's what we're going to do. We're actually going to factor by grouping. I'm so excited about this. I'm going to split this top into 2, right, to factor by grouping. Now look, you're going to simplify this, right? Algebraically, you still have to work with the variables. You must copy over that limit. Each time you don't, it's points up, okay? At every single step, you have to copy that over. So we factor this, and what are we going to get? So from here, we do x squared, and we get x minus 3 minus 4 x minus 3 over x plus 2. That's lovely. So this is the limit as x approaches -2 of x squared minus 4, x minus 3 over x plus 2. This is the limit as x approaches negative 2 of x minus 2, x plus 2, x minus 3. You see what happens? That x plus 2 went away. So that x plus 2 was what was giving us issues, and now it went away. And so now I have the limit as x approaches negative 2, x plus 2, I'm sorry, x minus 2, x minus 3. Now I plug in my negative 2, and I can drop the limit. So this is negative 4 times negative 5, 20. You see that? We made it go away. So at first we're like, oh my God, 0 over 0, the world's over. No, you get 20. No. But x doesn't equal negative 2. X is approaching negative 2. You see, this is limits. Okay. So here, when I plug in the 6 very quickly, I get 36 minus 42 plus 6 over 3 times 36 minus 66 minus 42. Guess what that is? 0 over 0. So we're going to factor. We have to do, you see, I plugged in the 6 here, no limit. Now I'm going to work with variables, put limit. Factor this guy, and I get x minus 6, x minus 1. Here I get 3x plus 7, x minus 6. So those go away. Limit as x approaches 6, x minus 1, 3x plus 7. Now I'm ready to plug in my 6. And I get 5 over 18 plus 7, 25, 1/5. Look at how cute. Look at how cute it turns out to be. Okay, so that's the first thing. Yeah. So next thing is rationalizing. All right, so the next way we can solve these is rationalizing. You're going to do these when you have a rational function and you're going to have a square root somewhere like this. Okay, so look at this one. When I put in the 25, right, do you see how I get 0 on top? And on the bottom I also get 0? So I need to rationalize this. This is where the issue is. So I'm going to multiply by root x plus 5, root x plus 5. And this is a lot less math than you actually think. So limit as x approaches 25 of, let's do the bottom first. It's a minus b, a plus b. So I square the first, I square the last, and it's what? X minus 25. Okay, I know now you have the urge to FOIL, as much as I hate that word, the numerator. Don't do that. Okay? What we're going to do is we're just going to leave it as is. It cancels out. It's really like the most beautiful thing in the world. Look, it just cancels out. Like, it does its own work for you. So now I have limit x approaches 25, root x plus 5. And now I can plug it in. Root 25 plus 5, 10. And people say like math isn't beautiful or like they don't like math. Give me a break. Okay, one more. What am I going to multiply this one with? Right, so 2 plus x plus 4 by the conjugate. So we're going to multiply. We're going to multiply out the part with the square. So again, square the first term, I get 4. Minus, now square the second term, and I just get x plus 4 over, don't multiply this. Okay? So, in the numerator, what am I going to get? So this is 4 minus x minus 4. What does that leave me with? Negative x over x times that mess. Cancel out the x's, but what do I have left in the numerator? Yeah, please don't let go of that negative 1, right? That's probably the most common mistake. And I hate to take points off for that negative when everything else was right. So now, look, now I can plug in my 0. And I get negative 1 over 2 plus root 4. Negative 1 over 4. Like, it's really a beautiful thing. I can't say that enough. Okay? Okay, so let's talk about limits at infinity. All right? Okay, look at these two functions here. The one on the left is an even function, right? Because they point in the same direction. Here, it's an odd function. One points up, one points down, okay? So when you have an even function, as x approaches infinity for this one, this goes to positive infinity. At negative infinity, this goes to positive infinity. So basically, at both ends, when it's an even function, they either go up or they go down.
When is it like infinity slash d&e, and when is it like just infinity?
So it's not just infinity, it's always infinity slash d&e. That's the case. And then for the odd function, both. We're going to do that now. For this one, here you get positive infinity or d&e. I think that's what you're asking. Here you get negative infinity or d&e. Now, we've touched on this before when we did end behavior. When you have a polynomial function, so for example, when you have, p of x is 3x plus 7 minus 2x cubed plus 5x. At infinity, the only one that matters is this. So you can throw away everything else and just focus on the term with the highest power. So why don't we do one here? Look at this. I have the limit. Now look at what's different here. It's as x approaches to infinity, right? Infinity. When I have this, I can throw away everything else and just take the highest power. Okay? Now, this is 4x to the power of 6. X is approaching positive infinity. When I put a positive number in here, will I end with a positive or negative value? Positive. So the limit here is positive infinity slash d&e. Okay? What about here? This is negative infinity. And again, I'm going to take the term with the highest power. If I put a negative number in here, in that circle, do I end with a positive or negative result? Positive. So this is positive infinity d&e. Yeah. What about this one? As x approaches negative infinity, now it's 4x to the 5. When I put a negative number in there, it's negative infinity d&e. What about this one? Yep, because it's negative. Yeah, cool. Okay. Here, this is the reciprocal function. As x approaches infinity, where does this graph go? 0. The limit is 0. Do you see how it levels off to 0? Right? So here, limit of f of x is 0. Okay, for the reciprocal functions. Let's do some of these and then I'll go over the, okay, here, okay, this is all stuff that we've done. So let's do some of these here. So 5, you know what? I don't think I have time for this. Do you guys, did we do this? Yeah, we did horizontal asymptotes before, right? Okay. When I do this, okay, so when I have rational functions, I have to compare the degree of the numerator and the degree of the denominator. All right? So look at this one. I just take the highest power on top, the highest power on the bottom. When the degree of the numerator is less than the degree of the denominator, right? This is what I get. And the limit will equal 0, right? Because it'll be 1 over x, right? And you have, yeah, it'll be 0. Here, when the degree of the numerator is equal to the degree of the denominator, you take the ratio of the leading coefficient. So look, negative 2x cubed, 6x cubed. This will be the limit as x approaches negative infinity of what? Negative 2 over 6. I'm sorry, negative 2x cubed over x cubed. So how much will that be? Negative 1/3, and that's your answer. And then when the numerator is higher, you get infinity or dne. Okay? So with that, I want you to do the homework here, part 1. All right? Have a great weekend. Thank you. Whoa.